This is a single grain of common beach sand. Inside it, we have learned to build a machine more complex than the entire city of New York, operating at the scale of a single atom. To build these superbrains, we start in the virtual cosmos. Designers write the logical architecture in code, which specialized software compiles into a gate-level netlist. This results in a detailed digital blueprint called a GDS2 layout, mapping out the position of billions of individual components. But a perfect digital map is useless without a flawless physical canvas. The challenge is that the universe does not naturally provide a surface pure enough for architecture this small. Natural silicon is full of microscopic impurities. To remove them, we chemically reduce sand into a gas and use fractional distillation to purify it to a parts per billion level. This hyper-pure silicon is then melted inside a quartz crucible at a blistering 1,425 degrees Celsius, a temperature high enough to liquefy most metals. Under a controlled argon shield, we dip a single seed crystal into the melt. As we rotate and slowly pull it upward, the molten silicon solidifies around it, matching its atomic lattice structure perfectly to form a massive monocrystalline cylinder called a boule. Sliced by diamond wire saws and polished to atomic flatness, this process yields the most perfect solid structure known to engineering, the foundational wafer required to house an atomic city. The next bottleneck is the printing process. The transistor pathways we need to draw are under 7 nanometers wide, which means standard waves of light are literally too thick to trace them. To bypass this physical limit, we use extreme ultraviolet, or EUV, lithography. This process utilizes light with a wavelength of just 13.5 nanometers to etch the circuitry. Creating this light requires high-power lasers to strike falling droplets of molten tin. These droplets are vaporized into a blinding plasma 50,000 times every second. Because EUV light is absorbed by almost everything, the entire process occurs in a high vacuum. We use atomically flat, multi-layered mirrors to bounce and focus the beam onto the wafer surface. If one of these optics were the size of Germany, its tallest surface imperfection would be just 1 millimeter high. By manipulating plasma and light at this extreme wavelength, we are able to etch nanometer-scale intelligence directly into the silicon. Even a perfect etch can be ruined by the environment. At this scale, a single microscopic flake of human skin is a catastrophic, city-crushing obstacle. To prevent defects, these chips are built in ISO Class 1 cleanrooms. Here, air is continuously filtered to remove 99.9995% of submicron particles. The room is bathed in a monochrome amber-yellow light. This specific spectrum is necessary to prevent the white light from accidentally exposing the sensitive chemicals coating the wafers.
Once protected from contamination, the wafer undergoes the chemical polishing and ion implantation steps necessary to finalize its primary architecture. But we are approaching a final bottleneck. Two-dimensional scaling is hitting the hard limit of atomic sizes. We simply cannot draw lines any thinner than the atoms themselves. To move forward, we are expanding into the third dimension, vertically stacking active silicon dies on top of one another. This requires incredible mechanical control. The machinery responsible for aligning these stacks accelerates at 5G and corrects its position 20,000 times every second. To link these layers, we use a process called the through-silicon via, or TSV. Solid copper columns are grown to pierce through the thin silicon, electrically linking the separate layers into a single high-density grid. This vertical integration turns a flat map of circuits into a high-performance 3D package, dramatically increasing processing power within the same footprint. Once the stack is encased in protective resin, it is seated onto a motherboard. We have moved from the scale of atoms back to the world of visible machines. This journey, overcoming extreme heat, manipulating ultraviolet plasma, and managing 5G of acceleration, all began with a handful of raw sand. By organizing matter at its most fundamental level, we have converted silicon into the high-speed processors that power the modern digital world.